If enantiomer and diastereomer labels feel manageable with one or maybe two stereocenters in a molecule, but completely unreasonable with more than that, this video will show you a nice shortcut that will save you a lot of time. In a previous video, we built a very comprehensive step-by-step method for determining if molecules were identical, enantiomers, or diastereomers, especially when the molecule had several stereocenters. In this video, I'll show you when you can move faster through the analysis and when you need to pump the brakes. Before we go any further, there's one important rule that must be met if we're going to compare molecules this way. They must be drawn in the exact same left-to-right orientation. That means the first bonds need to angle in exactly the same direction, the substituents need to be in exactly the same order, and it needs to have exactly the same left to right, up and down orientation. If they're not, then a shortcut fails and mistakes will happen. Once the molecules are aligned correctly, watch what happens. We only need to look at the stereocenter carbons. As long as they're drawn in the same orientation, if we go carbon by carbon, and every stereocenter carbon changes its wedge-and-dash orientation, the molecules are enantiomers. We could assign R and S labels to every single one of these stereocenters. That's beyond the scope of this video, but this stereocenter would be an R stereocenter, this one would be an S stereocenter, and in the other molecule, the bromine carbon is an S stereocenter, and the chlorine carbon is an R stereocenter. And notice that for enantiomers, every single R and S stereocenter changes its orientation. That's what it means to be an enantiomer. As long as they're lined up in the same orientation, this method saves you a lot of time. This method works no matter how many stereocenters there are in the molecule, as long as they're drawn in the same left-to-right orientation, and these molecules are not. So what can we do? We have two choices. The first, we can rotate one molecule to be the same orientation as the first molecule. If I do a steering wheel rotation of this molecule, I'll change the carbon orientation to being in the right orientation. And when I do the steering wheel, this fluorine on the bottom left will shift up to the top right, still on a dash. The chlorine that's in the middle will stay in the middle and it will rotate and still be on a wedge. And the bromine in the bottom right will rotate up to the top left, still on a wedge. Now they're in the same left to right orientation with the same connectivity all the way across. Now we can do a direct comparison of the wedge-and-dash notation. Here, I see the chlorine is the same wedge-and-dash notation, but the bromine and the fluorine have switched their wedge-and-dash notation. As long as they're drawn in the same perspective, if some but not all of the wedge-and-dashes change their orientation, then these molecules are diastereomers. It really is that straightforward, as long as they're drawn in the same orientation. If you feel pretty comfortable flipping and manipulating and rotating molecules, this may be the method for you. If you'd like a refresher on how to flip, rotate, and manipulate molecules, I have an entire playlist that I'll link in the description below. If, on the other hand, you feel you're much faster at assigning R and S, you can walk down the line and assign R and S to all the stereocenters. Again, that's beyond the scope of this video, but this first stereocenter is S, the middle stereocenter is R, and the one with the fluorine is S. In the other molecule, the bromine stereocenter is R, the chlorine stereocenter is R, and the fluorine stereocenter is also R. And again, we can see that some but not all of the R and S stereocenters have changed their labels. All of the stereocenters change, enantiomers. Some but not all of the stereocenters change, diastereomers. Let me make one more important point. For any given chiral molecule, it can have exactly one enantiomer, but it may have multiple diastereomers. Let me end by telling you when this method fails. We saw one minor failure point earlier. If the molecules weren't drawn exactly the same left to right, we couldn't just look at the wedges and dashes. The other time this method may fail you is for molecules that are structurally symmetric, that are palindromic, that are exactly the same left to right. If you've watched the other videos in this series, this has come up over and over again. If I were to compare these two molecules, they are drawn in the same orientation left to right, and all of the wedges and dashes change their orientation. So they look like they should be an enantiomer. But you must check for structural symmetry. If you notice the molecule is palindromic, you have to pause and take an extra beat. For molecules that are palindromic, the molecules that look like enantiomers may actually be identical. If I take this molecule and I flip it horizontally like a pancake, that's going to keep the carbon chain in the same orientation. And as I flip it like a pancake, this dash oxygen becomes a wedge oxygen, and everything on a dash becomes a wedge. This molecule that I thought looked like an enantiomer was really identical. What is the relationship between these two molecules? These molecules are identical. These are not two different molecules. This is the same one molecule, and it is drawn twice. 3 times, actually. Meso is the biggest stumbling block in this entire stereochemistry unit. It's a funny word to say, it's a hard word to define, and it's really hard to pick out meso molecules when they're drawn on paper. The biggest tip I can give you is watch out whenever you have a symmetric molecule that's palindromic. It may not be identical in meso. It may actually be enantiomers or even diastereomers, but you have to slow down and check. On exams, here's the safest approach. If you can manipulate quickly, manipulate the second molecule to be drawn in exactly the same orientation as the first. Then do the quick wedge-and-dash check. If all the stereocenters change, they're enantiomers. If some but not all the stereocenters change, they're diastereomers. Just watch out for structurally symmetric molecules that may end up being identical. Confidence comes from knowing when to slow down. If stereochemistry felt kind of like pattern guessing, it shouldn't anymore. Between the previous video and this video, you now have two methods for finding the relationship between molecules. The slow method that always works and you can trust, and the fast method that gets you the answer faster as long as you're careful about a couple of suppositions. That flexibility is what true OChemNinjas develop. You're not memorizing rules, you're building judgment. Keep up the good work, ninjas.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.